Hi, welcome to this course on data structures. Today, I'm going to talk a little bit about the analysis and performance of the implementations that we had done before in some of the previous lectures. In particular, the implementations of stack, queue, using underlying data structures in programming languages like C, like arrays and linked list. So let's try to clear some of the concepts using which we will be measuring the performance of various operations that we had implemented in C language. So the first concept is what is known as a big O notation. This is a very useful theoretical concept, mathematical concept that can be used to measure performance of various algorithms. A detailed description or knowledge about the big O notation and several other mathematical concepts which can be used to measure the performance of programs is out of scope of this lecture, but we are going to talk about two different big O numbers, which is order of 1 and order of n, to analyze the performance of various operations of stack and queue that we had implemented in the previous lectures using arrays and linked lists. So when an operation is said to be running with the performance of big O of 1, which is order of 1, it means that the worst case performance of the operation is independent of the number of input elements. So what this means is that if your collection has 100 elements, or it has say 1000 elements, or it has any arbitrary number of elements, say 2 power 100, whatever big number you can take, the operation is executed in same amount of time. So the operation is independent of the number of elements in your input collection. So this is one performance metric that we'll be associating with various operations. And order of n is associated with operations when the operations performance is directly proportional to the input size, which is the collection size. So if the collection has 100 elements, the performance of those operations which have order of n as their big O number would have a runtime of 100 into some constant c. If the input collection has 1000 elements, then the performance would be 1000 times constant. So in general, if the input collection has n elements, performance of operations with the runtime complexity of order of n would be constant times n. This is more of a straight line. The runtime of those operations which have order of n as a runtime complexity would be directly proportional to the input size, and they would increase linearly with respect to the input size. So in most of our operations where we are concerned about the performance of the operation, we would try to achieve order of 1, which is the best we can do in terms of the execution time. If this is not possible, we then try for order of n, which is the next best possible implementation time. Obviously, there are others in between these two, which is order of log n, but in our case, we'll have the performance as order of 1 or order of n. Okay, so let's start with trying to analyze the performance of various operations that we defined in the implementations of the abstract data types list, stack, and queue using arrays, linked list. And we have one more variation of linked list where we have an additional tail pointer, which helps us optimize some of the operations in the list, which we'll be talking about when we have to analyze it, and we'll do it separately. So let's start with the array implementation of list operations that we did. So let's start with insert at the start of the list using an array. So when you're trying to insert the element at the start of an array, let's take an array and there might be elements in the array already present, and when we're trying to insert an element at the start of the array, we would have to, as we understood, we would have to do a right shift of all the elements by one ordinal to the right. So this means that this is kind of dependent on the number of elements present in the array. This is more of order of n. And when you're trying to insert element at the end of the array, this is order of 1, because let's say we have elements present in the array and we're trying to insert it here. We already know the size of the array is at the end of the list in the array. So you just insert the element here because there's no shifting required to be done. This is more of order of 1. It doesn't depend on the number of elements in the array. Delete at the start is again order of n, because once you delete element here, you would have to left shift all the elements subsequent to that element that is deleted. So if there are n elements here, you have to do n left shift, so it's order of n. Deletion at the end is again order of 1. You need not do anything additionally in terms of shifting, just delete the element and just change the size. Get index is order of n because you need to compare each and every element in the array to get to the index of that element, so it's order of n. And get element is again order of 1. We already know that index based access is quite fast in this, so it's just order of 1. And size is again order of 1, is the size as we input the elements. Now let's try to understand the push operation. We were performing the push operation in stack by calling the insert at the start, so obviously push operation is order of n. Pop operation was also being performed by us by deleting the element at the start of the array, so this also is order of n. Top is again it calls get element at index, so this is order of 1. Size is again order of 1, we are maintaining size as well. Q insert in the array is order of n because we are trying to insert it at the start of the array. Q delete is order of 1 because we are trying to delete from the end of the array, so delete at the end of the array is order of 1. Now size is again 1. Now let's move to the linked list implementation. So we have a list variable, a structure which has a head pointer which points to the first node of the linked list, and then that subsequently points to the second node of the linked list, and so on till we arrive at a node that doesn't point to any further elements. So this is the snapshot of a linked list. Let's talk about insert at the start of the linked list. Start of the linked list is a constant pointer manipulation, so this doesn't depend on number of elements of links, so it's order of 1. And insert at the end as well is order of n because to insert an element to the linked list at the end, you need to traverse the links to get to the end of the list using the temp and the previous pointers, and as we had seen in our lectures. So this is order of n, which depends on the number of elements in the linked list. Delete at the start is again order of 1. It's just pointer manipulation, so you just remove the element and manipulate the head pointer to point to the element that's deleted, the next of the element that's deleted. So this is order of 1. Delete at the end also is order of n because you have to traverse to the end of the list to be able to do your pointer manipulation. Get index is order of n because you have to compare the element of each and every node with the given input element and then figure out the matching node's index, so we have to do traversal, so it's order of n. Get element is order of n again in linked lists because there is no fast array based index based access like arrays have, so you have to traverse and then keep a counter to keep track of the distance of each and every node from the head, and then as soon as the distance matches, that's your element, so it's order of n, depends on the number of elements. Size is order of 1 because we're maintaining it as per our implementation. For push and pop in stack, we're doing inserts and deletes at the start of the linked list, so both of them are order of 1. Top is order of 1 because top is primarily returning the get element with a value of with the input parameter of 0, so it will always run in a constant time. Size is again order of 1 because we're maintaining it. Q is insert happens at the start of the list, so this is order of 1, but deletion happens at the end of the list, so this will be order of n, and size is order of 1. Linked list with tail is an optimization, so it has the same performance as the linked list in all cases where you have order of 1 performance for the linked list. Now let's try to see the operations that are not performing well, which are taking order of n in linked list, and see if we can have the tail pointer optimize some of them. So to explain the tail pointer concept, what we also do in the linked list is have a tail pointer that points to the last element of the linked list. This tail pointer is maintained to the last element, in all operations like insert, delete, etc. So initially the list would start with head and tail pointing to the same element. There is just one element in the list, and as and when the elements are added to the list, tail pointer moves to point to the last element of the list. Okay, so let's try to see how insert works. So insert at the end for the tail pointer is order of 1 because we already have the last element's address in tail, so all we have to do is to point the tails next to the new element that we are going to insert at the end of the list, and point the next element of the new node to null. So this is constant operation. You need not worry about how many other elements are present behind the tail. So this is order 1. Delete at the end is not order 1. That's because so we just have pointer to the last element of the list. But for delete operation to be executed, we need to point the previous node of the tail to null, the next to the previous node of the tail to null. So this is essentially, this is pointed to null and this is deleted. So this again requires us to traverse from the start of the list because we are not maintaining the address of the previous node of tail. So fortunately, this also is order of n. It's not going to optimize the deleted then, although it's going to optimize inserted then. To understand getIndex, again, this is going to be order of n. It's not going to help with getIndex because traversal has to be done anyways, and getElement as well is order of n. And deletion of the queue is something that we have to see. So when we have the tail, again, deletion is order of n here because again, as we see, the deletion is something that is not optimized because we're deleting from the end. The queue deletion remains order. So this is the matrix that we have built. Now let's see if we can optimize some of the functions where the complexity is order of n. So let's look at the implementation of stacks, push and pop, which uses an array. Both of them seem to be order of n. Can we optimize these two operations? So let's take an array and see how if we can optimize these operations of push and pop for stack. So we're saying that we are going to insert the elements from the 0th index for push, and for pop we are saying we are going to delete elements from the 0th index. And this was required for us to maintain the LIFO order. The inserts and deletes of an array are not optimal at the start, but they are optimal at the end. So you have at the end you insert the complexity is order of 1. At the end, if you delete, the complexity is order of 1. We can just see if we can instead of inserting at the beginning of the array, we can see if stack would preserve its LIFO property if we are inserting and deleting at the end of the array. So let's say push of 1 happens. So this is the start and the end at the start because we don't have any element in the stack. So 1 is pushed here. And let's say push of 2 happens next. So that's order of 1. So 2 is inserted here. Push of 3 is the next element, next operation. So 3 is inserted here. And push of 4. So 4 is inserted here. Now let's say we have a pop of stack happening after this. So this is basically the size of the array after the insert of 4. Now pop would remove the element at array of size -1, which is 4 is removed. And is that expected that we remove 4? Yes, it is expected that we have to remove 4 because that's the most recently inserted element. So looks like this works so far. Now let's try to insert, let's try to pop again. Now what is the most recently inserted element of 1 to 3? That is 3. So when you pop 3, this seems to work, right? So one optimization that we can do to make sure push and pop of stack are order of 1 is to change your algorithm to insert and delete in the list at the end of the list rather than at the beginning. So this modifies our stack implementation a little. It's not much, it's a very simple change. So what you have to do is to say push of element in the stack is implemented as insert element size of the stack -1 comma list, or you can say stack, and push pop of stack should be delete size of s-1 comma s. So this way we have optimized the push and pop operations of stack. And now let's try to see if we can optimize so once we optimize the push and pop of stack, all of the operations of stack are order of 1, which is great news. Optimized. Now let's see if we can optimize the array implementation of queue. Unfortunately, I don't think it's possible to optimize it because queue has to insert its elements from one side but delete the elements from the opposite side. So if you're inserting from the left, you have to delete from the right. If you're inserting from the right, you have to delete from the left. So but then if you're talking about array, at least one of those inserts or deletes would have to take the hit of being the order of n operation. So if you optimize insert by inserting the elements at the end of the array for queue, you would have to take the hit for the delete because that has to now delete at the start of the array, and vice versa. So either this or this has to take the hit for the runtime, either the insert or delete. So for the queue, what we were trying to do with the linked list is that, let's say this is the list structure and then you have a linked list. We were trying to insert it at the 0th index, and then we were trying to delete from the end, from the linked list. The delete was not fine because you were not able to delete in order of 1, it took order of n, because you have to traverse and go to the end of the list and then delete your element by changing the pointers. But the insert was pretty fine. The problem with delete, as I said, is that even with your linked list with tail, the delete takes order of n. That's because you need to go to the end of the list and then have access to the previous node of the tail. We had performed insert at the start and delete at the end of the linked list. What if we change insert to be performed at the end and delete to be performed at the start? All we need to do is to make sure the FIFO property is honored, and this would lead to the optimization, because then what would happen is your delete would be performed at the start, which means it will be order of 1, right? Because delete is order of 1 at the start. So this will be converted to order of 1, and the insert at the end is also order of 1 for the linked list with tail. So this will remain order of 1. So let's now see if we can perform the insert at the end and delete at the start of the linked list and still preserve our FIFO order. So we have a list having a head element. This is our first node. So we have our list having a head element that's pointing to nothing, start of the list, start of the series of operations of the queue. So let's try to insert 1 into the queue. So this will be done at the insert is being done at the end of the list now, right? So this will point to a new node with the value 1. Now let's try to insert 2 into the queue. So this would again point to a new node, and this will be 2. Now let's try to insert 3 into the queue. So this will also create a new node. So the most recently inserted element is 3, but then the least recently inserted element is 1. So when we now call delete, 1 is the one that has to be removed. And let's see if that happens. So let's say delete is called now in the queue, and we are deleting from the start instead of the end, the opposite end to which we performed our insert. So this again is order of 1, because all we do is to just change the pointer to point to the next element of the node that we're deleting. So this node is deleted, and this looks to work fine. If you perform the next delete, all of what happens is that this is now the new node, and the least recently inserted element in the queue is 2, and that's what is removed. This works. Okay, so now with linked list with tail and a couple of changes in which we are now reversing the directions in which we are inserting and deleting elements into the queue, we can optimize the delete operation to order 1, and we can also optimize the stack array implementation to order 1 and order 1 by pushing and popping the elements at the end of the array instead of the start of the array. So we see how we have optimized some of the operations. They were not necessarily the most optimal solutions, but with minimal changes in the code, all we did was to change the index that is passed as a parameter to the list operations of insert and delete, and we were able to optimize the stack as well as the queue operations. So with that, I think this is the end of this lecture. We will meet in the next lecture with some of the practical applications of stack.